In the world of experimental physics, there's a fundamental truth we have to get comfortable with, and it's this: no measurement is ever perfect. Nope, not a single one. Every time we measure something, whether it's the length of a table or the speed of light, there's always a degree of uncertainty. So let's dive in and explore what that really means.
So let's just start with a really direct question to get us all thinking. Is it even possible to get a perfectly 100% exact physical measurement? Well, the short answer is no. And understanding why that is, well, that's the key to becoming a truly reliable scientist.
Here's the game plan for this explainer. We're going to build this whole thing from the ground up. We'll start with why uncertainty is, ironically, a certainty in science. Then we'll get into the super important difference between precision and accuracy. After that, we'll learn how to actually put numbers to these ideas, combine them in our calculations, and finally, we'll apply everything to some real-world examples. Okay, let's jump into our first section, the certainty of uncertainty. What we're going to do here is establish this foundational idea that uncertainty isn't just about making a mistake, it's about recognizing the built-in limits of how we measure anything. So, where does this uncertainty come from? Well, a few places. First up, you've got the limitations of the instrument itself. Every tool has a smallest measurement it can possibly make. We call that its least count. Think about it. A ruler with millimeter marks can't possibly measure micrometers. Then there's the skill of the person doing the measuring. A classic example is parallax error. That's what happens when you look at a needle on a dial from an angle instead of straight on. On top of that, the thing you're measuring might just have natural variations. And finally, maybe your equipment isn't calibrated perfectly. All these things together mean our final result is never just one perfect number, but a range of possible values. Now, let's move on to two of the most critical and honestly most often confused ideas in all of measurement: precision versus accuracy. Getting this distinction right is absolutely essential.
This table really helps break it down. Precision is all about consistency, or how exact your measurements are. It's tied directly to the least count of your instrument. The smaller that least count, the more precise your measurement. For example, using a micrometer to measure 2.455 millimeters is super precise. Accuracy, on the other hand, is about truth. It's how close your measurement is to the real actual value. And we usually judge accuracy by looking at the percentage uncertainty. The smaller the percentage, the more accurate you are.
The absolute best way to picture this is the bullseye analogy. Imagine you're shooting arrows. If all your arrows land really close together in a tight little group, you're being very precise. That shows great consistency. But if that tight little group is way off in the corner of the target, you're not accurate at all. The goal, of course, is to be both: a tight cluster of arrows right in the center of the bullseye. That's high precision and high accuracy. So we get the concepts, right? Precision, accuracy, we're good. But this is physics, so we have to speak the language of math. How do we actually put a number on this idea of uncertainty? Well, the most direct way is with what we call absolute uncertainty. It's really simple. It's just the smallest division your instrument can measure. Its least count. So if you're using a regular meter rule that has millimeter marks, the smallest bit you can be sure of is 1 millimeter, or 0.1 centimeters. That 0.1 centimeters is your absolute uncertainty. But that absolute uncertainty doesn't tell the whole story. An uncertainty of 1 centimeter is a huge deal if you're measuring a pencil, but it's practically nothing if you're measuring the length of a football field. It's all about context, and that's exactly where fractional uncertainty comes in. It gives us that context by making a ratio of the uncertainty to the actual measurement. You can see how the formula, delta x over x, captures that relationship perfectly. And to make things even more intuitive, we usually just turn that fraction into a percentage. It's just easier to grasp, right? A 1% error is something we can all understand instantly, way better than a fractional error of 0.01. This percentage uncertainty is really the key number we look at to judge a measurement's accuracy. The smaller the percentage, the more accurate the result. Simple as that. Okay, so we know how to find the uncertainty for a single measurement. But what happens when we use that measurement in a calculation, like finding the area of a rectangle or the volume of a sphere? Well, the uncertainties from each measurement have to be combined. This is sometimes called propagation of uncertainty, and lucky for us, it follows a few clear rules. Okay, rule number 1 is for addition and subtraction. It's straightforward. You always add the absolute uncertainties. Now you might be thinking, wait, even when I'm subtracting the numbers? And the answer is yes. Absolutely, because the uncertainty is a range of possible error, and that potential for error doesn't just cancel out, it adds up. So in our example here, when we subtract the two lengths, we add their uncertainties, giving us a total uncertainty of 0.2 centimeters. Now for multiplication and division, the game changes. Here, we add the percentage uncertainties. Why the switch? Well, when you multiply or divide, it's the relative error in each number that compounds and affects the final answer. Absolute uncertainties just don't scale properly in these cases. So, the method is convert each uncertainty into a percentage, and then just add those percentages together.
This next rule is really just a special case of the multiplication rule we just talked about. When you raise a quantity to a power, like when you cube the radius to find the volume of a sphere, you just multiply its percentage uncertainty by that power. So if your measurement for the radius has a 2% uncertainty, the uncertainty in your final volume will be 3 times that, or 6%.
All right, our final rule. This is for something we do all the time in the lab, taking a bunch of measurements of the same thing to get a better result. When we take the average of all those measurements, how do we figure out its uncertainty? We use what's called the mean deviation. This is just the average of how far each individual measurement is from the overall average. It gives us one solid number that represents the typical spread in our data. All right, theory's done. We've covered the concepts, we've gone through the rules. Now it's time to put it all together and see how this actually works by tackling a couple of classic physics problems. So here, we're calculating voltage with Ohm's law, V equals IR. That's a multiplication problem, which means we need rule 2. First, we figure out the percentage uncertainty for both the resistance and the current. Then we just add those two percentages together to get the total percentage uncertainty in our voltage. After we calculate the voltage itself, 39 volts, we figure out what 7.1% of that is to get our absolute uncertainty. And that gives us our final complete answer.
In this second problem, we have 5 different measurements for a single length, and you can see they're all a little bit different. That's that natural variation we were talking about earlier. This table just neatly shows each measurement, the average we calculated from all 5, and then the deviation, which is just the difference between each measurement and that average.
Okay, let's apply rule 4. First, we find the average of all the measurements, which, after rounding, is 1.21 meters. Next, we take all those deviations from the last slide and find their average. That's our mean deviation, and it comes out to 0.01 meters. And that value becomes the uncertainty in our final answer. So our best value for the length is 1.21 meters plus or minus 0.01 meters. So if you only take one thing away from all of this, let it be this simple idea. Precision is about your tool and its consistency. Accuracy is about your result and its closeness to the truth. Really understanding both is the absolute foundation of doing reliable science. And this all leaves us with a final, much bigger question to think about. If every single data point we ever collect has some uncertainty baked right into it, how in the world do we build these massive, trustworthy scientific theories like general relativity or quantum mechanics? It's a deep question, and it really gets to the heart of how scientific knowledge is built, all starting with understanding and managing the very uncertainties we've talked about today.